Let's take a look at first order partial derivatives as a sort of mixed review. When we're taking partial derivatives, we're looking at functions that have more than one variable. F of x and y where the variables are x and y. Could be x, y, and z. You could have two variables, three more variables. For this particular functions, we're looking at f of x and y, so the variables are x and y. Any other letters that we would see would be considered just constants. The notation that you see when you are looking at df over dx, they're really asking you for f sub x, the derivative with respect to x. When you see df over dy, they're looking for f sub y, which is the partial derivative with respect to y. So when we look at first order derivatives, they're asking us to take the derivative the first time at the first layer for every variable that you have. And for this function, again, it's x and y, so we're going to do it with respect to x. This first term has an x in it. With respect to x gives us 6x. The second term does not have an x. Its derivative is 0 with respect to x. The next term, minus 6x, derivative is minus 6. And these last two guys, no x's in them. That means they're constants. Derivatives of constants are 0, so we're done. When we look at now the partial order derivative with respect to y, this first term has no y in it, so its derivative is 0. The next term, minus 4y squared, has a y. Its derivative with respect to y is negative 8y. The next term, 6x, no y, so its derivative is 0 because that is considered a constant. Plus 10y has a y. Derivative is plus 10. Minus 40 is a number regardless of what you're taking the derivative with respect to. So his derivative is 0. And then you're done. Here's another function. It is a function of x and y, so we have two variables. We can see them there. Before we do anything, we know we want to rewrite this guy to be negative 4x to the negative 2 so that we can use our power rule. We need to find f sub x and f sub y, the first order partial derivative with respect to x, and the first order partial derivative with respect to y. So let's do f sub x first. 10x has an x in it. The derivative of that linear term is 10. E to the 6y, no x. His derivative with respect to x is 0. Next term, yes, there's an x. We have a derivative that isn't 0. Bring the negative 2 down times negative 4 is positive 8. X to the negative 3. Yes, you can rewrite that. Plus 8 over x cubed. If you're going to be doing second order partial derivatives, though, you're going to want to leave him like this. Now let's do the derivative with respect to y. Look at the first term. No y. X is a number. So because x is a number, 10x is a number. Derivative is 0. Next term, e to the 6y. There's a y there. We have a derivative that isn't 0. For exponentials, we rewrite him exactly the way he is. Chain rule out his derivative. Yes, it is okay to just go ahead and right away put that 6 out front. The next term, no y in it, so we are done. And the first order partial derivative with respect to y is this term. Here's the next one for you. Why don't you pause the video and see if you can do this one and then come back and look at the answer. Okay, we have a function of x and y, two variables. We're looking for the partial order derivative with respect to x. We notice both terms have an x in it, so let's take the first order with respect to x on this first term. When we do that, the y and the 2 are all numbers, so those are going to come along for the ride, and that's going to give us 2y squared as a coefficient. The x has a power of 1. His derivative is just 1. So we get 2y squared. For the second term, we have a power on our x. So we're going to bring that 2 down, multiply it by the 3 to get 6x. And the y is just a number. He's coming along for the ride. When we look at this derivative now, partial order derivative with respect to y, again, we have y's in both terms, so we're going to get two terms down here in our partial derivative. And when we do that, the first piece here with respect to y, the 2x is a number. It's just going to come along like it's a coefficient. We're going to bring this 2 down, multiply it by the 2 to get 4. So we're going to get 4xy as this partial order derivative with respect to y. So 4xy. For the next one, 3x squared is a number, and the derivative of that with respect to y, it's really like the coefficient of y, so we get 3x squared. This function is embedded within a root, so we're going to need to rewrite that. 7x plus 3y to the 1/2. And now we're going to take the partial order derivative with respect to x. That x function is embedded inside that square root. So we're going to use the extended power rule and the chain rule. Bring the 1/2 down. Keep what's inside. Subtract 1 from the exponent. 1/2 minus 1 is negative 1/2. Then we chain out the derivative of what's inside with respect to x. So the 3y, his derivative is 0, but the 7x gives us a derivative of 7. Yes, we can write that 7 times the half to go 7 halves, 7x plus 3y to the negative 1/2 to set ourselves up for taking another level of partial order derivatives. Let's go ahead and do f sub y. Again, we've got this y embedded inside the function, so we're going to need to use the extended power rule and the chain rule. We're going to bring the exponent down, keep what's inside, subtract 1 from the exponent. Let's go ahead and do that. Bring the 1/2 down, keep that function that is inside, subtract 1 from the exponent. Then we're going to chain rule out. And it's with respect to y because that's the variable we're working with. And 7x has a derivative of 0 because x is a number. 3y has a derivative of 3. We can go ahead and rewrite that. Gather the 3 out front. And you're done. Here's another one you need to rewrite. When you have rational functions, you're going to want to make them negative exponents so that we can use our power rule. And doing your first order partial derivative with respect to x. This has one term. It's got an x and y in it, so we're going to have a partial order derivative for x and for y. When we do it with respect to x, the y is a number, and so it is just going to come along for the ride. So that gives us y to the negative 1. The derivative of x is just 1, so we are done. Then we can take the partial order derivative with respect to y. The x is a number or coefficient, so it comes along for the ride. The derivative of y to the negative 1 is bring the negative 1 down, subtract 1 from the exponent. And you can rewrite that to be done. So sometimes they look a little odder than others. This is our final one where we have a natural logarithm. We have a function embedded inside. There's an x in the first term, not in the second. There's a y in both terms. So let's keep our eyes on that. Let's take the partial order derivative with respect to x. When you have a natural logarithm, the derivative is 1 over what's inside. That's everything that's inside the logarithm. And then you multiply by the derivative of what's inside with respect to x, because that's what we're working with. And the first term, 5xy, take the derivative with respect to x, 5y. And minus 6y squared with respect to x is 0 because y is a number. And yes, you can rewrite that. You could factor out a y as well. And I'm going to just leave it like that and let that to you. F sub y. Now there's a y in both terms of the expression inside the logarithm. The derivative is still 1 over what's inside, so you rewrite everything that was inside. Do not take a derivative in this step. You're just taking a copy of what's inside the logarithm. Now we need to take the derivative of what's inside here with respect to y. So this is with respect to y because of this guy here. So 5xy with respect to y is 5x. Minus 6y squared with respect to y, bring the 2 down, negative 12y, 2 minus 1 is 1. Yes, you can rewrite that, 5x minus 12y over 5xy minus 6y squared. That one's a little bit more complicated, the common error and what you want to be careful of. It's 1 over what's inside, so it's the entire expression that comes here. Then you chain rule out the derivative of what's inside. 1 over what's in here, chain rule out the derivative of what's inside. Be really careful. This guy in this denominator must be exactly what's here. So that's it. Hope you're having a great day.